and beyond. Space, in partnership with the European Space Agency.
Twinkle, twinkle, little star, how I wonder what you are.
When it comes to the origins of the universe, there's one idea that really captures our imagination. And it goes like this. Everything, even time itself, started with the Big Bang. So, is that what really happened?
Twinkle, little star.
The Big Bang is something in our current thinking as the point of origin where our universe came into being. How that happened and what was exactly there at that point in time is still not very much known.
The Big Bang is an idea. I would say it's not a moment in time, and that's what I think often people confuse Big Bang with a certain moment in time.
The universe becomes infinitely dense and infinitely hot at the time equal to 0 seconds. And so this is what's called the Big Bang.
The Big Bang is a model, and it's a model that allows different factors which have been observed to be linked and given a sense. And it allows us to have developments in theory that can be tested against observations. So it's a model that allows us to create a story.
If the concept of the Big Bang is tricky to describe, then it's even more tricky to measure and test with scientific experiments. But that's exactly what two of the major projects of our time set out to do. One of them is on Earth and the other in space. Here on Earth, that experiment is at CERN near Geneva.
This is it. We're standing in front of the detectors which were used last year to discover the Higgs boson.
Two science teams worked in parallel with CERN's Large Hadron Collider to find the fabled Higgs boson, the particle that gives mass to matter and proves the existence of the Higgs field.
We believe this experiment can help us to understand the Big Bang. If you look at it, the energy level we reach and sort of the masses we could reach in creating this experiment, we should be going to something like a billionth of a second after the Big Bang has happened. So very, very close by the Big Bang.
While tiny particles collide at CERN, the European Space Agency's Planck satellite sits far out in space on an epic quest to scan the remnant light from the Big Bang. In spring, the Planck team released what's considered the ultimate map of the cosmic microwave background. It shows the universe as it was just 380,000 years after the Big Bang.
The satellite is in an orbit which is following the Earth from a great distance. And as it follows the Earth, it goes around the sun. And so that big circle that the camera is making on the sky is also turning around the orbit. And with a combination of these motions, we can build an image of the whole sky over about 6 months.
To get to the heart of the matter, finding out how matter, everything in the universe, came into being, requires big-scale science experiments. And for the particles in this 27-kilometre loop, it means a dramatic end.
Particle starts off inside a bottle of hydrogen.
They're like a swarm of flies which are flying through this beam pipes.
By the time it's in the LHC, it's going at 0.99999999 of the speed of light.
They typically will be circulating in this machine for the order of 8 to 10 hours.
finally the proton will collide with a proton coming the other direction and be destroyed, and its pieces fly everywhere, and hopefully making some new particle as it does it.
The universe expands enough for these charges to...
The photons, or particles of light, that constitute the cosmic microwave background lead a quite different life. So where have they been before they're picked up by Planck?
13.8 billion years. Let's start at the beginning. In an inflationary universe, you've got a tiny patch much smaller than even the nucleus of an atom that inflates and makes a universe that is as big or even bigger than what we can observe. And a photon that lives in this early universe travels and scatters off of positive and negative charges because the universe is so dense that you've got a plasma with positive and negative charges. And photons scatter around. Eventually, the universe expands enough so these positive and negative charges, electrons and protons, turn into hydrogen atoms. So the photon stops scattering around and goes on a straight line, keeps going for 13,800,000,000 years until it hits the mirror of the Planck mission and ends up in one of our detectors.
Light that travels to us from the dawn of time and particles smashed in a giant accelerator. These are the witnesses we rely on to reconstruct the story of the Big Bang and all that followed. But are they telling the same story?
The Planck satellite is a great achievement. They've been studying the way the universe works, and they're finding connections between the model that we have and what they're observing. It's all very intimately connected. In one sense, I think we're learning the rules that the game's played on, and they're more working out the way it actually worked out in our universe. But without either piece, you're only seeing half the picture.
Clearly, at the fundamental level, there is a very deep connection, right? I mean, for example, we want to know what dark matter is. And dark matter probably is some kind of particle that we know very little about. So that's, for example, a very clear connection with the particle physics community.
Certain models that we can construct are totally compatible, can be brought together, if you like, to describe the Higgs found at CERN and, let's say, the inflationary properties as they were measured by Planck.
Inflation, the set of theories that describe a universe that expands exponentially fast for a fraction of a second after the Big Bang, is supported by the Planck data. However, our picture of the early universe is far from complete, and there are plenty of outstanding questions and anomalies.
If we try to calculate based upon the partial picture we have today, we do find very big contradictions in some places. For example, the Higgs field, we've discovered now this Higgs boson. The Higgs field is supposed to give mass to all the universe by filling the universe with this field so that particles have mass because they're always moving through this stuff. This Higgs field is extremely dense. It's far, far denser than lead. And yet, somehow, we don't see it. It's not out there affecting the gravity of the planets. So there's a big contradiction between what you think you're learning about a field filling the universe from the particle physics side, and from the astrophysics side, it's quite clear that the universe is not filled with a liquid much, much denser than lead. So there's definitely a conflict there, something we need to understand.
There are different kinds of anomalies, and some of them are really at the very largest scales. For example, we see that there is an asymmetry in the amount of power there is in one hemisphere versus another. It's a very specific hemisphere of the sky versus the other. And this should not really happen according to our theory.
Recent theoretical developments are a bit troubling. That's to say, there's a trend in theoretical physics that thinks that the universe we can observe is just a small part of an immense universe. And we are seriously considering that there's another part of the universe that we can't be in contact with, that we can't measure, which obeys different laws, including the fundamental laws of physics. And that's quite sad when you think about it, because it means we may end up with an explanation like, well, things are like they are because they're like that.
The science goes on. The Planck team is now studying polarization patterns, and the CERN scientists will probe the Higgs field further when they switch the LHC back on. Both are at the frontier of research into the origins of the universe, a frontier of both theory and data.
For the time being, I would say for the next 20, 30 years, we have a lot on our hands to get to understand and to move on, collect new data to help understand what happens there.
This incredible wealth of data and observations that we can use to confront these crazy ideas with, that's really what excites me about this.
That's the way science works. I mean, we look for the edge. What is it that we don't understand? And then we scratch away until we find something that allows us to understand it.
It's not unfeasible or not unthought of that maybe at some point the human brain is simply not grand enough to capture what is really behind everything.
Twinkle, twinkle,